Okay, so now we talked about average velocity and instantaneous velocity. Let's just make sure that your minds are on about rate of change. What is a great rate of change and what is a lesser rate of change? If you actually have a graph that goes like this, and I'm going to pick, let's say, a couple points here. Now the rate of change on average, so the average rate of change from here to here, is equivalent to this, to the slope of this secant line. Okay? Now, that is basically saying how high am I going for every single one that I go over? How far up am I going for every one? Now let me take two other points on the same curve. Let's consider, actually this same point, and we'll make this point right here. Do you think the average rate of change will be greater or less? Well, let's take a look. If I draw a line from here to here, I think we can all see right away that this line from here is going up farther by the time it gets over here to here. It's going up more. So the slope, that means each step that we're taking, we're going up a little bit more for each step. So the slope is greater. If you want the greatest slope that we'll talk about is almost vertical. Right? It's like basically the highest slope you can get is pretty much vertical. Right? As this goes down, we go lower and lower and lower. That means that the slope is getting smaller and smaller. So just by looking at points, you can tell which one has a greater slope without even calculating. If I'm comparing two slopes, just look at the lines and you can see which one has the greater slope. It's less, 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 less. Some people think this is the least you could possibly get. This is the smallest slope. But in reality, this is a slope of 0, and we know that we could go below 0. We could go -1, which would be a 45-degree angle, -2, -3, -4. As a matter of fact, we could get almost back to vertical downward, and that's the least slope you could ever do. Okay? Let's find another place where the instantaneous rate of change would be about the same as the rate of change from this point to this point. How would I do that? Well, I could actually just observe and take a look at this. I see the slope of this. When would the instantaneous, let me redraw this curve, the instantaneous rate of change be about the same as this? So it's going to go on this angle. It might be higher or lower, but it's on this angle. Right? So it's not going to go like this, it's not going to go like this. It could go like that. It would be parallel to this line. So let's find a spot on this graph. Well, the slope's going to be like this, like this, like this. I'm following right here. Here's the slope as it's getting lower. It looks like right about here, it looks like this tangent is getting pretty close. Maybe there's a point right about here. No, I'm just guessing. Maybe there's a point right about here where this tangent is actually parallel. I tried to make it parallel here. They're parallel. They're actually parallel to each other. Are there any other points? Well, as soon as I go beyond this, it looks like it's not going to be parallel anymore. And it keeps going. Now we're way off. We're practically perpendicular, actually. And now we get, as we come across this bump here, the slope is actually moving back. And there's going to be some spot here where it's parallel again. I would say about this point right here, we actually have another line. Well, that was not even close. Another line where it's actually parallel again. Okay? Which means they have equal slopes. And on this bump, again, we're going to get another one that's going to have another slope that's like that. And eventually, on each hump, we're going to get another one. So there are actually several places on this graph that have a slope that's equal to this secant. Can I find another secant with an identical slope? Well, sure I could. I just find it's a point that's lower, make sure that I have the same slope as that, follow that line, and just find another point here. And sure enough, again, it is parallel, it is the same slope. What about a perpendicular slope? Absolutely. This is perpendicular like this. I just have to make sure I find a spot where it passes through 2 points on the curve. I don't really have one. Yeah, so I guess we're not going to do it on this one. But let's say this curve actually came like that. Then I could say, oh, look at here. From here to here, we have a slope that is perpendicular. Now I'm just using my eyes. I'm not using, it's just the concept of it. When we use some math and we have some equations, there will be other ways. We know that if they're perpendicular, then the slopes will be negative reciprocals of each other. And if they're parallel, their slopes will be identical to each other. What else can I talk about? So a negative rate of change, by the way, is any rate of change is below the parallel, so it's heading downward, like this, like any of these. Once you get to this is a zero rate of change, it's staying the same, and positive rate of change. Word problems. How do you distinguish whether to use average rate of change or instantaneous rate of change in a word problem? For me, it seems pretty simple. If they're ever asking you about 2 points in time, so what is the average between this time and that time? Then we're talking average rate of change. Or what is the rate of change from here to there? We're talking average rate of change. But if they only state in the problem one spot, so they say, what is the average right at this time, or right at this moment, or at this level, or whatever it is, if they only name one, then we only have 1 point. We're obviously going for the instantaneous rate of change.